So yeah, today is about unbottling the secrets of knowledge distillation. This is, instead of giving a very broad overview, this is now a very niche, and it's going to be a quite technical talk, so more focused on the literature and less presenting a tool. But of course you can think of this being used in a tool. But I would also claim that most AutoML pipeline in the end, if they want to achieve state-of-the-art, would use something like this in the background. So yeah, thanks for having me. I'm looking forward, and I hope that at the end of the talk, all of you, if my voice stays with us, have a nice overview and understanding of knowledge distillation, where it comes from, and how to apply it in a state-of-the-art setting. First, very small motivation. I guess I can pretty much skip this one because everybody uses ChatGPT or some sort of foundation model nowadays. But pretty much since 2021, there has somewhat been a shift in paradigm. And now whenever we start a machine learning workflow, instead of pre-training on a big data set, which if you look at, I don't know, Lion 5 billion, which I think is like 200, or like, I think Lion 5 billion has 240 terabyte. The Domo, so the open source language data set, is around 4.5 terabyte. And if you think about the big models, they're only roughly 100 gigabytes. So they can neatly fit on a disk, and they already comprise the internet knowledge, essentially. So think of a big foundation model as nothing else as a compressed version in a neat format of a very large data set. So how do we leverage this? Before I go into this, there needs to be, I promise this is the only advertisement slide. Our personal motivation why we're looking at this at Bosch is, of course, we want to have AI in all kinds of products. It is actually pretty much in every product that we have. AI is either in the product or used during the development of the product. So it's pretty much everywhere. One use case is pretty obvious, autonomous driving. There we can't have a big foundation model running in the car because you want to have a very quick reaction time, and you also want your car to drive when you don't have Wi-Fi or internet. Another fun use case is an oven that we recently deployed. There are two customer pain points where I guess everybody can relate to this, that it's annoying to constantly stand up and check the food, whether it's ready or not. And the second pain point is that the oven has many settings. So we deployed a small, so this is somewhat of an MNIST use case for us. We deployed a small camera in there, and it does now food recognition. So when you put your pizza in the oven, it recognizes it's a pizza and selects the best heating section, which I learned is double underheating and grill from the top. And then you also have a browning detection, and you can select your preference. Then you get a message on your phone when your pizza is prepared according to your preferences. So that's a small use case where we also use knowledge distillation in some of the tools. But on a high level, foundation models are painfully slow to run, and we very often need task-specific models, have latency constraints, memory consumptions, and we also care about the climate. So the problem setting is very general. We want to go from the big, slow foundation model to a fast, task-specific online model. Before I go into how to do this with knowledge distillation, I will give a very brief overview of prior methods. But I guess they've been mentioned here, but just want you to have a complete overview that this is not the only compression method. You're all aware of quantization. I guess this is pretty much straightforward. What also came out big in the last couple of years was low-rank approximations. Those are mostly relevant for training time reduction. So what you do there, you have your big foundation model, and you project your parameters from the large parameter space into a smaller space where you essentially learn. And the smaller you make it, of course, the faster your training is, but also the less flexible your model is. The other method is obviously pruning, where you cut away neurons that you don't need. Of course, you need to do this in a structured fashion to really benefit you on the final, on the GPU, on the target hardware. Obviously, we also have neural architecture search and architecture optimization in general. Since this is usually a separate slide deck and this talk is planned for 1 hour, I didn't include this in here, but I'm pretty certain you heard about this on Wednesday from Aaron, if I know the schedule. Okay. Yeah, and then compact and efficient model design. To be very honest, this is still what brings improvements nowadays by a factor of 10 or 100. So of course, we use auto-tuning pipelines, and they're very good initially, but when we really want to tune something for a car where millions of people use it, we really want to over-train and over-engineer this network. And they're really looking at the hardware, looking at how the memory is dealt with, and so on. So far, AutoML doesn't save us there yet. So this compact and efficient model design is where a lot of work still goes into. Knowledge distillation, I will talk a bit. The last method that is orthogonal I would like to mention that I really like is a dynamic sparsity. If you think about the brain, and I'm talking right now, I guess not your whole brain is activated and needed for understanding what I'm saying. So depending on what happens, different parts of your brain are activated. Loosely, this only has been implemented in neural networks in the recent years successfully, even though it was already pitched, of course, in the 90s. So, without further ado, let's really deep dive into knowledge distillation, look at the literature, and gain an understanding of how it works internally. I've prepared a small story. This story essentially consists of 5 acts, like a nice drama. And let's start building an intro of the important characters, and then, of course, creating some sort of conflict. We looked at the bigger field. There are a ton of compression methods. Knowledge distillation obviously also consists of thousands of papers. We're looking at a very small part of knowledge distillation, which is called response-based knowledge distillation and feature-based knowledge distillation. I'll get into a second what this exactly is. Let's start at the original motivation, and I really like the original paper, so let's take a look into the brain of our godfather, the Nobel Prize winner Geoffrey Hinton, who pitched this originally and has a really weird motivation for this. So I guess he sees, so this is literally the introduction from the paper. So he claims that nature deals very different from how we train neural networks. So the training phase he somehow compares to a larval. This is when a fly grows. And there it has a very different scheme in terms of how it's built and how it's used. And later, during deployment, when it's a fly, it's optimized for traveling and reproduction. So if you look at neural networks, we can see the networks have the same shape during training and during inference. It's the same network. And what we want to have is we want to have larvae and flies. Sorry about that. That's the motivation. I would have never come up myself when I look at flies and larvae, but this is essentially the root of knowledge distillation and where it stems from. So the way it's implemented here is during training, we use a very large network, which we all know larger networks are better in terms of optimizations. There's less saddle points. There's always a better escape to go to minima. Not local minima, but one of the minima values, as we all know. And then during the forward pass, we can compress this. So if the claim is correct, at the end of the talk, I should present you a method that trains better if using this big network instead of using just a small network. So let's see whether this is true. Okay, so how does knowledge distillation actually work? I motivated it quite a bit. Here we have obviously a pipeline for supervised learning. We have a loss where we have 0, 1 labels for cats and dogs in this example. I'll talk about images, but this applies to languages, tabular data, everything. But I always think images are the easiest to explain things with, and I like cats. So let's change this into a knowledge distillation setup, and instead of getting the label from the human, in this case, which you can also think about some sort of knowledge distillation from the human brain to the model. However, here we get it from a foundation model. And if we look at the logits, it's not 0, 1 anymore. We have smooth logits. In the setting, we usually have 2 terms. We refer to the big model as the teacher and the smaller model as the student. And PT I'll use for teacher logits, and PS I use for student logits. Sometimes also probability, sorry about that. You can have optionally latent losses, which is kind of nice because this gives you additional guidance system. And that's also where the teacher-student analogy breaks down a little bit, because if you look at the school, you can't give the students access to the teacher brain internal state. The teacher is usually frozen, so it doesn't require as much memory, and the student is trainable. Here the student probabilities in this case. And then as a loss function, most commonly we use the KL divergence, but of course we have a stop gradient where the, is this one? We have a stop gradient operator for the teacher, since we don't want to have gradients there. So yeah, what's the benefit of knowledge distillation? Because so far we can also just use human labels and they're available abundantly. And here this original proposal on dark knowledge came out, that if we look at cats versus dogs, for human labels or typical data sets, this is usually a binary labeling scheme, but with the teacher you can really probe the decision boundary and therefore also see what is in between. So this dog I found on Google kind of looks like a cat to me, and the network also reflects this. So this dark knowledge is supposed to be the guiding system according to Geoffrey Hinton. So let's look into this hypothesis. And as I promised earlier, the title of this part is now "The Inner Workings of Knowledge Distillation Remain Unclear." So this is built on the paper with already the, I guess, intensive title, "Does Knowledge Distillation Really Work?" The setting is as before. We have a teacher, we have a student, and we try to match the probability logits in this case. And yeah, I think it's a CFAR, so it's image classification, so it's very simple. Just matching of outputs between teacher and student as explained before. Now as a tool to understand knowledge distillation, they introduced this notion of fidelity. So this means, okay, let's hope that doesn't happen. They introduced this tool called fidelity, which essentially means how true is the student to the teacher. So how much does it obey and really listen. And if knowledge distillation would really work, in the end, of course, the student should imitate the teacher, which we would expect because we train it to. And that's what they use to like tackle this dark knowledge hypothesis. And now, somewhat counterintuitively, in the beginning, they found that the teacher the student does match the teacher, and we have 100% agreement. However, if we train with more and more data, in this case generated with a GAN, and also in case of having multiple teachers, we see that the agreement somewhat goes down. The first claim would be, okay, hey, in the beginning it's overfitting and this is a clear sign of memorization. However, the student and the teacher are the same network. So the student should have the full capacity to approximate the teacher. So what should we try? If we think it's overfitting, of course we train for a very, very long time. And usually 300 epochs, here they tried 5,000 epochs. They got a slight 2% increasement in train agreement, but they never got the teacher, the student to actually really do what the teacher does at all times, which with such a small network on such a small data on this amount of expanded samples, you would expect it to. They also, of course, tried different optimizers and so on. Looking at the test agreement, you would also expect this to fit, but here they also claim you only get up to 80% agreement between a student and teacher. Let's make this very extreme. Let's say we have a random teacher, and let's say we want to approximate the random teacher. We can do this here, shown in this case. And they introduced this notion of lambda. You can think of lambda as how close the student initialization is to the teacher initialization. So if you recall correctly, the student and the teacher are the same network. If we initialize them identically, of course, the problem is trivial. And the more different we make it, the harder it is. And here they find this point at lambda equals 0.25, where the student can still approximate the teacher, but if we go beyond this, it somehow seems to be an optimization problem that we cannot solve with current methods. And this was the state in 2021. So what they claimed in the end, does knowledge distillation really work? We know from countless benchmarks in the past that it does improve the performance, but here they claim that it fails to live up to its name. So the student doesn't really replicate the teacher. So now there's the big question of why does it work then? Why does it improve the performance? And yes, please.
Very quick question.
Yes.
Are you now saying that knowledge distillation in general improves the performance, or is it mainly to because you've introduced it as I'm trying to make the model smaller?
Mm-hmm.
So, is it now that you're trying to improve the performance of the teacher model, or is it you're trying to bring this by retaining as much as knowledge, bringing it into this model?
It's a good question. Ideally both. So we're always on a Pareto front between runtime and performance. And knowledge distillation is pretty much used to squeeze out the most performance out of a small network. So usually a network is given and specified by the constraints such as the target hardware and the runtime. And let's say those two things fix the network architecture. And then we really want to overtrain this and squeeze out the most performance, because we know it's only trained once, but it's used in inference for a long, long time.
Okay, so the idea is, irrespective of how large in the paper you just showed, they use the similar size model, right? So the idea there was how close can we actually get? And so irrespective of what the model looks like, the idea is to retain as much as information as possible by transferring, and ideally we might even gain performance.
Exactly. And yeah, this was only for investigative methods. So this is more of an ablation study, which also fits for the next paper, which actually goes into the extreme of the question you just asked. Quickly explaining the setting, the knowledge distillation papers are unfortunately always a bit inconsistent. Here they use the teacher and the student logits and compare them. However, they also use the true labels and use a loss there, and I think alpha is 0.5. And now they run a set of experiments that shouldn't really work. So we have the vanilla setting, we have a large teacher and a small student. However, they also reverse this, where the teacher, here it's called student, I don't like it in this paper, but the teacher is small and the student is the big network. And they also have a very poorly trained teacher. So they introduce a bunch of ablation studies to understand this a bit more. And what they find, sorry, this table is quite full. I'll go over through it in a second. They find that this reverse KD actually helps, even though it should harm. So here we have our baselines of the student parameter. We have the teacher networks for the reverse KD. And we see even if the vanilla KD, of course, improves, but also if you look at this, at the reverse KD, we see this also improves the performance. And the same for the defective KD. So if you look at the teacher performance, like here it's even just 15%. If they use this together with the labels, important detail here, they also improve the performance. So something is counterintuitive. Why does a bad teacher help? Yes, please.
When you say defective KD, does it mean that it's trained on mislabeled data, or does it have information that is false, or is it not trained?
I think it's trained only very shortly, but to be honest, I would have to look in the paper. But both would be possible.
Improving performance now means I either train it like my student model directly on the data and compare it to be trained on the teacher, or I'm not improving the performance of the teacher. Right?
The teacher is always fixed. The teacher is frozen. We don't touch this.
So what do I compare the performance?
Do you compare the performance to, it's just the student? Sorry, the student baseline is just the student trained on the data. Sorry, student baseline, that's a good question. So here student baseline is normal KD, and the numbers are the same. Not sure what, the student baseline in this case is either trained on labeled data or with vanilla KD. So in order to understand this, they thought maybe the pitch here is that the teacher is just some sort of regularization in this case, and our training might be a bit noisy. So what they look at is, we said they use the true labels and they use the teacher logits. And as we recall, there's also in this KL divergence with the softmax, we also have a temperature. So they look into this temperature, which is usually a parameter that is also tuned. And what we see from the plots from left to bottom is increasing temperature. So just looking at the blue bars, if the temperature is very low, we know it's very peaky. And if we go towards higher temperatures, it gets less peaky. And if we would go to infinity, it would, of course, be uniform. And as a comparison, they also plot a uniform distribution. So what we see here is that it somehow matches a uniform prior if we go towards this regularization with knowledge distillation. So blue is knowledge distillation and orange is just a uniform prior, hard-coded. Nothing happens there. So the question they ask now is, can we do just label smoothing, and does this match the performance? And they now call it teacher-free knowledge distillation. I think label smoothing is a bit simpler. And what they show is that normal knowledge distillation matches the performance of just doing regularization. And this paper, I think, is from 2022 or something. At the time, this was a big impact because there were quite a few knowledge distillation papers using exactly the same technique. And they're saying, like, hey, if you just do label smoothing, we get a similar performance. And now, I guess we're at the peak of our conflict, and we're somehow dissatisfied that knowledge distillation doesn't live up to its promises. However, in the very beginning, I, of course, already teasered a bit that this is a state-of-the-art training method. So let's see what is different. Let's look at a knowledge distillation paper that has, or had in 2024, I think, the state-of-the-art, already in 2022, the state-of-the-art on ImageNet for a fixed architecture. So let's say we only look at, as you said, a constrained network architecture. In this case, it was a ResNet 50 and other predefined networks, and try to squeeze out the most performance there. And yeah, the setting here is, again, the student just mimics the teacher. We don't use the training labels. And they introduce two concepts which are sadly surprisingly simple. One is patience and the other one is consistency. So let's understand those two buzzwords. So I'll take some time to explain this because this is the core message of the paper here. So in the beginning, we have the prior method of a knowledge distillation where we have a fixed teacher. And here we have the student logits on the top and the teacher logits on the beginning. Very often they're pre-computed to save some time, and the augmentations are just applied to the student, which is why we have a small spread here, and then it's supposed to match the teacher. Nobody does this, but for some reason this is also in this plot, is if you apply different noise to the student and a teacher, maybe you could do this to introduce some invariance. And what they want to introduce here is so-called consistent teacher, which is straightforward, but it's a small but very important detail. Use the same augmentations for the student and the teacher. And the third one here, so this, if you look at this plot, it's now the same box that goes into the student and the teacher. And the last one they introduce is, they now call it function matching, because I guess if you want to have a new paper, you need to give it a new name. But essentially what it is, they also use mix-up augmentations and also make them consistent. So if you look in detail, what they want to highlight here is that also in between the dots, they now have interpolated samples. So if you, as a quick reminder, mix-up augmentation is just you take, let's say, an image of a dog and a cat, and you interpolate them. And you also interpolate the labels usually. However, here they just use the teacher. And the way you usually interpolate the labels is linear, but this might not be true. And with the teacher, you can just probe the decision boundary, and the teacher is somewhat the oracle that tells you how to traverse there. So consistent is explained. This just means same augmentations for teacher and student. Yes, I think explained this, mix-up augmentations, and yeah, same random crops and other augmentations for teacher and student. Let's look at the results. On the left side, we just compare it to regular supervised training. So the green line here is the knowledge distillation for them, and the other ones are various versions of a supervised training. I currently see it's commented, so I'll mention it here. They also compare to other state-of-the-art training pipelines like big transfer. They're already really pre-trained on big data sets and so on. And this is still superior and actually also more compute efficient if you really want to get the best performance out of a given network. And what I really like is that they train for a long time and they never overfit. So this is now like 4,800 epochs on ImageNet and here 9,600 epochs on ImageNet. As a quick reminder, I would say with this setup, I would say you get 200 epochs out of a V100 GPU in 1 week. So multiple GPU weeks, months, we're talking here. The cool thing is if they used an even better teacher, they were able to achieve at the time a state-of-the-art performance on ImageNet and even improved this by quite a bit of margin. So somehow Geoffrey Hinton might have been right after all, that this setup with the larvae and the training should be different. And if we then use it during deployment, we end up with a more effective model. Now you could say, okay, hey, before I showed this, it doesn't work on CFAR. It might be due to the data set. Unfortunately, I think they didn't do CFAR here. However, they did other small data sets and also showed that knowledge distillation with lots of data augmentation and having a good teacher really boosts the performance. And so the orange line is always the baseline, the red line, so baseline in terms of trained on the data set itself without the teacher. And the red line is the teacher performance. And yeah, knowledge distillation is a very helpful ingredient if you do it right. So now we loosened the tension a little bit more. The observation here was that they can get state-of-the-art performance in a single network. Let's understand this and also wrap this up a little bit by looking at why this didn't work in the previous data sets and why it works now. And this is where the vanilla KD paper comes in, and you can think of this as somehow going back to the roots. And this is just standard knowledge distillation again, just response-based. We have the setting here again, we have the logits of teacher and student, and we also have the labels which are used again in this case. And they also compare a little bit to hint-based knowledge distillation, which should in principle give you a clearer signal, but is also a strong inductive bias which involves many design decisions, like which layers to connect and so on. The goal here is to show the effectiveness of just vanilla KD if done correctly, and also explain the prior results with the so-called small data pitfall. So what they did here is they looked at CFAR again, and here's the performance gap compared to vanilla KD. So they always compare to vanilla KD and dist and DKD. I won't go into detail, just think of them as a fancy knowledge distillation method where quite a bit of brain power went into. So strong inductive biases in a more abstract language. On small data sets, putting in inductive biases helps, as we all know. However, if you go to larger compute and more data, you can already see where this is going at in the end. We see that less inductive biases and a more abstract formulation help, or more simple. Think of the intermediate losses and so on also just as inductive biases or constraints. And an optimization problem with constraints is always more difficult, especially if you have infinitive data and compute. Yes. Mm-hmm.
Can you explain again what we can see, like what are we comparing here? Like
yes.
Knowledge distillation versus distillation.
Yes, thanks for asking. I always like questions, by the way, so please interrupt me at any time. So on the x-axis, we increase the amount of data. Yeah. On the y-axis, we have the performance gap, and the performance gap is always dist, which is a knowledge distillation, minus vanilla KD. And here DKD minus vanilla KD, and here we see that dist is better because there's still like a positive performance gap. If you go to more data, it's negative. Thanks for asking. The message is more data, more compute, less inductive biases. The less performance gain you can achieve if you introduce essentially brain power on a very abstract sense. So keep the formulation as minimal as possible if you have large amounts of data and large amounts of compute. Very abstract, abstractly spoken. Yes.
So just on a slightly different perspective.
Mm-hmm.
So I'm trying to understand what happens with the information. So like what type of information is being lost when we're distilling the model? Is it like a hard question, like the hard choices when the difference between the probabilities are like 60-40, or is it some abstract information that we cannot really comprehend?
Mm-hmm. That's a really good question, actually. We should look at this. I don't know whether I have a good answer for this right now. I would need to think about it. I can only give you a loose answer. So we often know that if we distill on like just a certain domain, we lose generalization capabilities. So there is some drop of information, and we only distill this on like, let's say, the support or the data we train on. If the support is already so large that the capacity of the student is the bottleneck, then it's a really interesting question what drops first. I would guess it does some mode collapse usually, but I don't know.
Yeah, maybe like some sort of like, if you take latent space and you kind of like dimensionality reduction, you kind of like project the entire network in a smaller network, and you kind of like have some interference between like two features. But then again, in the information, like empirically, we wouldn't know like which cases a distilled model would be worse at, and which cases like it would actually perform good.
Yeah, I mean, in the linear projection case, I would say it just goes towards the PCA and like goes to the top eigenvalues depending on what's the rank. But in the nonlinear case, I think it would be interesting to look at. I don't know whether this has been done before. Yeah, this is essentially repeating what we said. So here we have the setting that we have a teacher, which is ResNet 44. ResNet 18 is the student. And if we look at previous training recipes, so training for a short time, we see that the previous methods, which have stronger inductive biases, are stronger. However, if we train with a longer or more powerful recipe, which just means more augmentations, still patient and consistent, essentially vanilla KD is on par. Let's look at some more details. I would need 5 to 10 more minutes. I hope this is fine. Okay. And really take this to the extreme. Let's see how much performance we can squeeze out of a single ResNet. So as a quick reminder, I think before it was something like 81, 82. Then the patient and consistent paper came out. They were able to boost this to 82.8, I guess. And this is a long-standing benchmark. So really many people try to bite their teeth on this one. And they were still able to bring those boosts, which I found pretty impressive. So 2023, they asked again to this now, or at the time, I would say 11-year-old benchmark, can they still improve it? First, quick reminder, here they compare hint-based versus logit-based, so intermediate representations that are compared versus outputs. And if you compare the hint-based versus the output-based, we see that the output-based win a little bit and are a little bit superior. So simpler is better in this case. Here I mentioned this already earlier, we're training for a very long time. So we're talking about weeks on a single GPU. Of course you can do this parallel. And the big question is, when should you stop training? And so far, I would say this question is not fully answered, because the longer you train, the more your performance increases. But of course, you have diminishing returns. The bottom line is, if I can recommend a setup here, in the end, I would really recommend knowledge distillation. Because it's fully flexible, like with quantization, with pruning and so on, you always have some sort of constraint of how to design the student architecture given the teacher. And with knowledge distillation, we have this very strong setup, and of course we can also do quantization combined with it, and also do quantization in the second step and so on. Yeah, that's, of course, they also took this to an even larger compute, and the last thing I would like to highlight here is that it's always the same pipeline. It's no additional data. It's not pre-trained on anything. The additional data is only in the teacher model. And they were showed that with this simple pipeline, with really 4 different networks, they were able to squeeze out state-of-the-art performance, which I really like because it's simple and very effective. I have now, if I can click to the next slide, I have 3 wrap-up slides. One, I guess all of you could have seen coming, is somewhat Sutton's bitter lesson that haunts us here. So we just went to bigger networks, more compute. We boosted the data set only by augmentations. I mean, of course, the teacher has been trained on a big pre-training data set, but for fine-tuning, which in most cases we are doing, and the foundation models are almost available abundantly nowadays, those are the only ingredients we need. And we can get the most out of a given task and have our nice embedded network for whatever application you're planning on, also in your private hobby projects. Yeah, this concludes somehow the story. But so far we only looked at compute and augmentation. However, there are other design choices, and for the sake of time, I will skip the long story behind it and directly jump to the results. So if you look at the typical training pipeline, there are, in this case, 7 different decisions where we need to make design choices, or hopefully the AutoML pipeline does this for us in the future. And looking at this, also given the fact that the training is very long, and we also know the fidelity on shorter training, so estimating the performance of a long training with a short training is somehow tricky. There's still a lot of manual design here involved nowadays. And here to go through the quick messages is, here we saw in the literature that a bigger teacher usually helps. Obviously it's slower because a bigger teacher takes longer in the forward pass. But there were a lot of claims in the literature also saying we need to have intermediate teachers. There shouldn't be a large gap, like a toddler wouldn't learn from a professor. However, we found that the better the teacher, the better the student if we train for a long time. We haven't gone to the full extreme, like really toddler networks. But also I tried to fiddle with this in a linear case, and I couldn't find a solution where the best labels wouldn't lead to the best solutions. But if you can come up with something here, please approach me. The other design decisions, KD loss, just output matching, hint-based losses are unnecessary constraints. There's a lot of literature also on cross-architecture knowledge distillation, so transformer teacher, CNN student with different inductive biases. And we also found that XKD usually just works if you train for a long time. Augmentation, strong and consistent, we mentioned this. Another thing I would like to mention, because papers often introduce fancy methods, if we look at the variance in performance between teacher choices and like other things, what is the most important is tuning the hyperparameters, the learning rate and those things. Usually the variance there is larger than the small decisions in the end, so those also need to fit. Okay, last slide. Okay, the second is a goodbye slide. So last slide with content. The summary in the beginning, we talked about different compression methods, and then we focused on knowledge distillation, and we have the story with building the conflict in the beginning. where we have two papers that criticized knowledge distillation, but later we were able to explain this away by saying this is a small data, small compute pitfall. And in terms of an effective methods, we already saw like flowers on a data set with only 1,000 images. With small data and high compute, we can already train very efficient and effective networks. And in the large data sets and large compute regime, it's now a state-of-the-art method, and it's pretty much everywhere. If you think about the smaller DeepSeek models, the QN models, and so on, it's always, there's a knowledge distillation section in each paper. I hope all of you have somehow a good understanding of knowledge distillation. And with this, I would like to thank you for your attention.